All right, so we're talking about stereoisomers, and the only qualifications for a stereoisomer, it has to be non-superimposable, but it has to have the same constitution, right? Your carbon has to be bound to A, B, and C, right? And so there's two options here. One, we could be enantiomers, which is what we've been discussing, and these are mirror images, right? But they still have all these qualifiers before them as well, right? They're non-superimposable, same constitution, mirror images. But we can have stereoisomers that are non-superimposable but are not mirror images. Those are called diastereomers, right? So these are not mirror images. Right. And of course, all the qualifiers go for this one as well. So we already saw an image of a diastereomer when we did our alkenes. Right, the cis versus the trans, right? You can see that these are indeed stereoisomers. They're non-superimposable, but they have the same constitution. But at the same time, they're not mirror images. And so these are diastereomers. This can also happen with our sp3 carbons in some special situations. So for example, if we had cyclohexane like this, and then we're going to add an alcohol group over here, so we'll call this OH, and then we'll add a methyl group right here as a CH3. And then if we think about drawing its enantiomer, all we have to do is put it in the same position and just switch both of these wedges into dashes. And if you think about the right or left-handed, maybe pause the video, figure out whether these are R or S. You should end up with an R up here, an S here, and then an S, and then an R, right? You see that they've flip-flopped, right? They flipped, and so these two are enantiomers of one another. If you think about it, they are indeed mirror images, but they are not superimposable. So they are enantiomers of one another. But we could draw other versions of this cyclohexane with with an alcohol and methyl substituent. So for example, we could draw this, right? Maybe one wedge up here, or maybe a dash up here, and then a wedge down here, right? And so if we think about the relationship between these two, they're not mirror images, right? This one has both up, this one has one up, one down. They can't be a mirror image of one another, but they still have the same constitution. And so they are stereoisomers of one another, or they are diastereomers, right? So they're stereoisomers, but not mirror images. And then, of course, we could draw the enantiomer of this. We could just put this in the same position and then just flip-flop the wedges and the dashes. And, of course, you can see the R and the S's. So you can label this and this top one, they're both S. And this bottom one, they're both R. You can see how they've switched, and you can see all the differences, right? On the left hand, we have an R-S pair. On the right hand, these enantiomers are both R or both S, right? So you got to know the relationship between this stuff right here. Let's go ahead and do another example. So we put an alcohol here, maybe a CH3 here, and then a chlorine here. And then we could take a look at another molecule, right? So this is going to be a similar molecule, but I'm not going to draw it in the same orientation. So in this case, I'm going to put this alcohol over here, this CH3 over here, and then this Cl over here. And now I want to know, what's the relationship between these two molecules? Are they enantiomers of one another? Are they diastereomers of one another? Is it the same molecule? Did I just draw the same molecule twice? And so obviously one way is to mentally rotate all this stuff in your head, but as you can see, that's going to be pretty easy to make a mistake. The other way is to label all of our stereo centers as R or S, and so we're going to go ahead and do that. Maybe you want to pause the video and do this yourself. You should end up with an R up here, S, and then S, right? And then over here we have S, R, S. And so then if you compare all of our stereo centers, they've all switched, right? The alcohol went from R to S, the methyl went from S to R, and then the chlorine went from S to Whoops, my bad. This one should be an R. Whoops. Went from an S to an R. And so they all switched. And so this is an enantiomer of one another, right? And so we could redraw this molecule on the left here. Let's go ahead and do that real quick. And then compare it to a different compound. So let's go ahead and take a look at this. Here we're going to put this chlorine as a dash here, this methyl as a dash here, and then this OH as a dash here. And so this one might be easy to tell that it's probably not an enantiomer because it doesn't have the same number of things facing the same way, right? Not two wedges or two dashes, but we can still label them, right? This one gets an S, this one gets an R, and then this one gets an S. And so if we take a look at the alcohol, oops, it went from an R over here to an S over here. So that looks like an enantiomer over here. And then if we compare this methyl, it goes from an S to an R. So still looking good over there. And then finally, this chlorine goes from an S and now it stays an S, right? So they didn't all switch. We have different R's, we have different S's. They didn't all flip-flop. And so that makes these a diastereomer. They're still isomers of one another, but they're not mirror images of one another. And just as an FYI, the maximum number of stereoisomers something can have is going to be equal to 2 up to the power of the number of stereocenters. So if you have one stereocenter, you're only going to have one stereoisomer or 2 stereoisomers. If you have 2 stereocenters, that's 2 squared, you'll have 4 stereoisomers. And all of these stereoisomers are going to come in pairs of enantiomers. Right, so be able to differentiate between an enantiomer or a diastereomer. Let's take a look at one more example. We'll again use the same molecule we've been using, right? So OH, CH3, Cl, and then R, S, S. And then I'll go ahead and draw another molecule right here. OH, CH3, and Cl. And so you might be thinking, oh, okay, we got, 2 wedges of dash. Maybe they're enantiomers, right? They both have 2 up, 1 down, or vice versa. We can go ahead and label these isomers, right? And this is, or these stereocenters, this is an R. This gets an S, and this gets an S. And then if we compare it, the alcohol has an R, the methyl has an S, and the chlorine has an S. They're the same. And so these two are actually the same molecule. And it makes sense if you have this kind of plane right here. And then if you flip this 180 degrees, you'll see what happens, right? This alcohol that was kind of going to the back of the board will be coming out of the board here. And so it'll look the same as the other one, and then vice versa for the methyl and the chlorine. And so they end up being the same molecule. But you can see on this piece of paper, they don't look the same. And so that's why you need to be able to identify whether these stereocenters are left or right-handed.